Today, we're going to verify that the modifications we made to the stock camshaft on this 670cc Predator-powered 1969 Renault will solve our massive oil leak problem. Plus, we're going to modify and tune the twin 24mm carburetors to see if we can solve the exhaust gas temperature anomaly that we're seeing with the thermocouple probes. And then we'll wrap this video up with a performance test to see if this silly car will go any faster. Stick around if you want to see if this Predator swapped contraption can go any faster than a diesel garbage truck going up a hill. Alright, let's get started. I reckon we actually need to put this engine back together before we can test drive the car. Now, the good news is, this engine's very simple and it won't take long to reassemble it. Now, I've been elbow deep in all kinds of engines over the years, and I have to say, on this engine, the castings and finished surfaces appear to be very well done. Predator engines in general are clones of successful Honda engines. From what I can tell, this engine's not an exact copy of a Honda because it uses different gaskets for the case, but the overall design is similar to a Honda. So this is the stock modified camshaft that we featured in the past few videos. Initially, we pulled the cam out to completely remove the compression relief mechanism, and if you haven't seen those videos, well, the short story is, the engine has no problem cranking over with full compression, and removing the compression relief is a valid modification if you want to lower the idle speed of the 670cc engine. But keep in mind, completely removing all traces of the compression relief gizmo introduces a huge problem with the crankcase ventilation system, and we found that the steel slug that was inside this hollow camshaft has to remain in place. Otherwise, the engine will gush oil from the crankcase vent. Now in our case, we went with a simple solution and cleaned the inside of the cam and coated the steel slug with Loctite and jammed the slug back into the camshaft. Once the Loctite cures, the slug is permanently bonded to the inside of the cam, and in theory this will keep the oil from leaving the crankcase with authority. Now all that's covered in the previous videos, but here's something that popped up in the comments. You know, I have to laugh because when I made that video, I inadvertently did a Jedi mind trick when I said, if I zoom in, we can clearly see these 4 grooves that are carved into the block. Well, pay no attention to those. Those are intended to supply oil from splash lubrication to this side of the camshaft. Apparently, that's exactly what a lot of people did, and I got a bunch of comments similar to this. Sort of like when old Ben Kenobi said,
"These aren't the droids you're looking for."
Anyway, for some reason, either by the Jedi mind trick or some other higher power, a lot of folks missed how the cam gets lubricated, and they were concerned that bonding the slug inside the cam would disrupt the oil flow to this side of the camshaft. Well, no worries. This side of the cam gets lubricated by these notches via splash lubrication. Bear in mind, the inside of this engine is not like a warm, calm beach somewhere in paradise. It's more like a Category 11 never-ending rainstorm. It would actually be a miracle if something didn't get splashed with oil inside this engine case. So, is the Jedi mind trick real? Let's find out. You will subscribe to my channel. You will feel compelled to click on the like button. Now, I promise I'll use the Force for good and not cross over to the dark side and start preaching about how great Subarus are. No doubt you folks noticed I'm applying assembly lube to the various parts as I assemble the engine. Meh, I use assembly lube, other people may use motor oil, and some people use nothing. I like assembly lube because it sticks to the surface that it's applied to for a long time, so if it takes me a couple of days to assemble an engine, the lube will still be in place, whereas motor oil may drip back into the engine case. The cam slots into place right here with both timing marks lined up. Due to the gear ratio between the cam and the crankshaft, the cam spins a lot slower than the crankshaft. To be more precise, the cam spins exactly 1/2 speed of the crankshaft. Now the case gasket seems to get damaged every time I open up the engine. This time around I smeared grease on the gasket. This is a trick a lot of people have suggested, and it's based on the advice from Thunderhead 289. The grease should help the gasket remain in one piece if I need to take the engine apart again. So as you can see, the side cover is on and I've inserted all the bolts. Now here's something to keep in mind if you ever open up a 670cc engine. These 2 bolts are slightly longer, and the easy way to remember where the longer bolts go is they're in the area where the dowels are located. Since this cover is a structural part of the engine block, it's important to torque them to 17 foot-pounds to maintain the integrity of the overall assembly. Now here's something curious I discovered on the engine. Over on this side, we have an arrow pointing down, and over on this side of the engine, we have an arrow pointing up. My first thought was, this engine must have been assembled incorrectly at the factory. But as it turns out, this is correct and the arrows are pointing in the right directions. In case you're wondering, the pistons are manufactured with an offset wrist pin, and the arrow direction is important. Now, if you ignore the arrows and install the pistons incorrectly, well, that would cause the cylinders to wear out prematurely. Now, several people have left comments suggesting that since the heads are off the engine, I should go ahead and possibly clean up the ports. Well, I'll be the first one to admit that I know nothing about porting an engine, and I truly believe porting is a form of art. Now, at first glance, these ports look to be massive, and the castings seem to be perfect. But then again, I'm no expert. It's possible someone with a keen eye could spot something that needs to be improved, but I certainly don't. And what I mean by that is, there's nothing obvious that jumps out and screams, "Take a grinder to me!" I think basically I'm just not qualified to touch these ports, and perhaps I'll just leave them alone. So the head gaskets that came with this engine appear to be in excellent condition. Now these are MLS or multi-layer gaskets. You have two steel outer gaskets and an aluminum inner gasket. This seems like a lot of thought went into the engineering of this gasket system. A lot of people have suggested that these gaskets can be reused, and by the look of them, I reckon they're in near perfect condition. However, just for fun, we're going to try something a bit different and use a set of copper head gaskets. This is a single layer gasket of the same thickness as the multi-layer gasket, so we won't be getting a boost in compression. Now, according to the vendor, these gaskets were annealed after they were cut, so we don't have to worry about annealing them. But for some reason, the vendor recommends that these be coated with a layer of copper spray, and they recommend the copper coating cure for about 12 hours before installing the gaskets. So I'll go ahead and shoot 2 coats of copper spray on each side of these gaskets, and then let them cure for the recommended time. Fast forward 12 hours and the gaskets are ready to install. I went ahead and put them outside and let them bake in the mild autumn sunlight. Assembly is straightforward. These head bolts are original to the engine and there's no reason to replace them since they aren't torqued to yield. I went ahead and torqued the bolts in 3 steps until I reached the recommended torque spec. The rest of the engine assembly I did off camera, and all I really did was install the push rods and the rocker arms. Now, when I disassembled the engine, I made sure to label the rocker arms and the push rods so they could be installed in their original locations. On a lawnmower engine with such low hours, who cares? But it's good practice to always assemble used parts in their original location, especially on automotive engines. So even though this is a simple throwaway engine, I made sure to put it back together exactly the way it was built from the factory. Now off camera, I'll go ahead and install the 4 bolts that hold this engine in place. Fast forward a few minutes and the engine's bolted to the cradle and it's been topped off with fresh oil. Let's crank it over to prime the oil pump and get the engine ready for its first start. That should do it. Now we can install the carburetors. If you've been following this project, then you likely know that we've upgraded this engine with a set of 24mm OKO carburetors. Today, we're going to modify the carburetors by adding a nipple to this location here, and it actually looks like this carburetor was manufactured with provisions for nipples, so that's good. Now the reason we're installing the nipples is so we can connect the carburetors to a set of gauges in order to synchronize both carburetors. And later in the video I'll show you how that's done. Anyway, right now we have to drill and tap this carburetor for an M5 thread. I believe these carburetors are made from a zinc alloy, and that means the metal is very soft, so drilling and tapping will be a breeze. And the nipple screws in like this. So here's something interesting. These nipples require a 9mm wrench to tighten. I reckon this is the first time I've ever used a 9mm wrench. You know, I've always wondered what the purpose of the 9mm wrench was, and now I know. I'll go ahead and do the other carburetor off camera. So this engine uses a custom 2-into-1 header with unequal length primary tubes. It's similar to the exhaust on a Subaru Boxer engine, and that's what gives Subarus that awesome sound. Anyway, in the previous videos, we were seeing a difference in exhaust gas temperatures that's close to 200 degrees Fahrenheit on our thermocouple probes. So let's go ahead and weld in some bungs for a wideband sensor for each of the primary tubes in order to measure the air-fuel ratio for each cylinder. This modification to the exhaust is, well, it's temporary and will only provide us with the air-fuel ratio at idle. The reason this is just temporary is the wideband sensor is way too big and blocks about 50% of the exhaust flow in each of these primary tubes. Now, normally we run the wideband sensor at the collector, which is a much larger tube, and it doesn't impose any restrictions to the exhaust. I think it'll be interesting to see what the actual air-fuel ratio is on each cylinder at idle, and perhaps we can solve the mystery of why we're seeing a difference in the exhaust gas temperatures between the cylinders. Now, I have the tools and the wherewithal to do a deeper dive when it comes to measuring the air-fuel ratio, but most normal people tune carburetors by ear and throttle response, and of course checking the spark plugs. The old school method is still top-notch, but since I have the tools, well, let's take a closer look. The twin carburetors that we're using were more or less perfect right out of the box, and I only needed to reduce the size of the pilot jets to get a more reasonable air-fuel mixture at idle, but for most folks, the original jets would have been fine. The bungs are going to be welded onto the primary tube as high as possible in order to have enough clearance to fully install the sensor. It would be nice to have permanent sensors on each primary tube, but that's not possible with the current exhaust system. Now, I can come up with a list of reasons why my welds are not perfect, but ultimately it boils down to, well, I'm not a professional welder. And of course it would help if I kept the visor clean on my welding mask. Meh, these welds will be good enough. And we're done. The area around the bungs have been painted with a high temperature paint, and the reason I painted the welds is, if there are any leaks, I'll be able to see the contrast in the paint where the carbon from the exhaust spills onto the gray paint. Fast forward a bit, and off camera I confirmed the engine runs and there's no issues with oil leaks and whatnot. We have the wideband sensor set up to measure the air-fuel ratio on this cylinder, but before we start fiddling around with fuel mixtures, I want to establish that both carburetors are synchronized. Now these gauges are connected to the nipples that we just installed on the carburetors. Basically, these gauges read the vacuum on each cylinder. Now, it's important to remember that this is a basic low-compression lawnmower engine and not a fancy motorcycle engine. The ignition timing on this engine is not adjustable, and there are hard limits to what we can do to this engine. The gauges will help synchronize the carburetors. However, there's a lot more that could be done if the engine was more advanced. Unfortunately, since this is a simple low-cost engine, we can only adjust the carburetors and nothing else. Also, remember our primary goal is to have the lowest idle possible so the transmission can engage properly, and the idle speed will affect the vacuum as well. Let's have a look at the gauges. At idle, it's pretty close, but watch what happens when I give it the beans. Yeah, we definitely have an imbalance at part throttle, and it looks like the throttle cable on the left carburetor has too much slack. This is something we can definitely fix. To adjust the slack in the throttle cable on this carburetor, all we need to do is raise the height of this thingy. Let's see what happens. That's pretty close. It's amazing that with the right tools, you can see problems that would otherwise be totally invisible. Okay, now we fired up the wideband air-fuel sensor and we're looking at the mixture on this cylinder. Also, the top number on the thermocouple gauge is the exhaust gas temperature on this cylinder. The air-fuel ratio actually looks okay for an air-cooled engine, but over here we are seeing the cylinders running slightly colder. Very interesting. Well, I'm going to say cylinder number 1 is close to ideal. Let's take a look at cylinder number 2. As you can see, I moved the wideband probe over to this cylinder. Once I start the engine, it'll take a few moments for the sensor to warm up before we can get a proper reading. And that looks about right. Now, I make this look simple, and for the most part it is. However, there's a lot of adjustments, and in total it took about a half hour of fiddling to get both carburetors balanced and to get the idle air-fuel mixture as close as I could. Let's put the wideband sensor at the collector and take a look at the mixture of both cylinders. So the idle mixture is slightly rich, but still in the ballpark for an air-cooled engine. Both carburetors are synchronized at idle and part throttle, and unfortunately we still have an imbalance as far as the exhaust gas temperatures go. I'm going to call this a success, despite the weird readings on the EGTs. Let's go ahead and take this little French car for a ride. Finally! You know, the best part of my day is when I get to drive one of my crazy contraptions. Okay, so the engine's been warming up for about 5 minutes, and the good news is it's still running. The crankcase ventilation system appears to be dry, and that's more good news. I'm sure the rest of the car is in tip-top shape and we have nothing to worry about. After all, it's a 55-year-old French car that hasn't seen a lick of maintenance in the last 40 years. The transmission slides into gear with just a hint of resistance. I really don't think we can get the idle to go any lower, so that's as good as it gets. I reckon good enough is better than, something. Now, today we're going to be using an external microphone that picks up the sound of the exhaust. And trust me, listening to the exhaust is a lot better than listening to the noise inside this car. It seems like the new interior camera is picking up all the rattles inside the car. The car's running really good, and the way the transmission's set up, this makes a great in-town car, but we're actually going to be heading out of town so we can run the engine pretty hard. I want to make sure we have no more issues with the oil leaking from the crankcase ventilation system. Now, I apologize, the lighting isn't ideal this time of the day, and it may be hard for you to see the speedometer. So this time of the year we get millions and millions of birds that like to migrate south for the winter, and for some reason they like to get in my way. You would think a butt-ugly French car that's barreling down the road would be enough to scare anything, but not these birds. And if that weren't enough, we have marsupial deer that run around like they're insane or something, and they're attracted to the chrome plating on my front bumper. I don't know why they have to stand in front of the car, but they do. Anyway, fortunately, this time of the day, it's just the birds we have to worry about. So if you're new to the channel and you made it this far into the video, well, thanks for hanging in there. Now hit the subscribe button and consider becoming a patron. The link to my patron page is in the video description. So yeah, this car does have a 4-speed transmission. However, the way it's set up, we only use 3rd and 4th gear. If it helps, I can change the shift icon to look like this. Now we have fast and faster. Actually, I can leave the car in faster or 4th gear all the time and the car drives fine, but it's a little bit slower on acceleration. That's why I like to start off in fast and then shift to faster. I hope that makes sense. And nope, this isn't a French thing, although I wouldn't put it past them. It's just the way I built the car. If you're interested, check out the older videos on this car if you want to learn more. Anyway, it may seem like the car only has 2 speeds, but since it has a CVT type clutch in it, it has an infinite amount of speeds. Multiplied that by 2. That's basically how I'm able to get this car to go down the road with a lawnmower engine. Actually, this car is a lot faster than most go-karts with the same engine, so that's something, I guess. Just for fun, let's see if tuning and synchronizing the carburetors had any effect on the acceleration. The time to beat is 22.68 seconds for the 0 to 50 and 29.46 seconds for the 0 to 55. Not too shabby. We shaved about a second off the 0 to 50 and just a little bit more than 2 seconds off the 0 to 55. The twin carburetors really help out on the top end of the RPM range. Let's see how fast this buggy will go. Normally I don't drive this thing faster than 60 miles per hour because, well, it's not very stable at high speeds and it feels like the wheels are made out of marshmallows. 69. Nice. I reckon it would have gone faster, but for that we're going to need a longer road and possibly a stunt driver. So performance is not bad for a 2-cylinder engine from Harbor Freight in a car that's shaped like a brick And keep in mind, this thing weighs 1,800 pounds plus the driver, so we're asking a lot from this little 670cc engine. I don't recall how fast the supercharged diesel Honda is, but I think this Renault would give it a run for its money. Well, once again, this completely useless car has not failed to impress. You know, it doesn't look like much, but we just made the Kessel run in 12 parsecs. So yeah, it's fast for a lawnmower-powered car. Let's take a look and see if we busted anything. So far, so good. Not a drop of oil from the crankcase vent. Let's take a look at the drive system. Typically, if we're having problems, there'll be a buildup of dust in this area as the drive belt starts to disintegrate. But since we upgraded to a Comet 94 series clutch last summer, we haven't seen any signs of belt wear yet. And that's good, because this belt is pretty expensive and costs about the same as maybe 5 or 6 pizzas depending on your location on this planet. Overall, things are finally looking up for this car. Alright, I reckon we should head back to the shop before the rush hour traffic gets any worse. So occasionally I'll see a comment where someone asks what's the purpose of this project, and I guess that's a valid question. Well, there is no purpose other than to have some fun with small engines. I reckon the Predator V-twin that we're using is better suited for a go-kart, and some people have actually put them in golf carts. I prefer to build street-legal go-karts, well, because they're more comfortable, and with a proper tag on the back of our go-kart, we can more or less go anywhere. Now, I like to drive at normal speeds, and given the weight and less than ideal aerodynamic shape of this car, well, the fuel economy isn't exactly stellar, and the car seems to only get 35 miles to the gallon at highway speeds. But keep in mind, this is not a fuel economy project, and 35 miles per gallon ain't bad for a 4-door go-kart. Anyway, the camshaft modification we made in order to reduce the idle speed of the engine initially had some drawbacks, but it looks like we were able to solve the problems. And now we have a much lower idle speed, which was ultimately the goal. I had fun today, and I hope you did as well. We'll see you next time. Until then. Knock, knock. Who's there? Subaru. Subaru who? Knock, 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 knock. Get it? Oh boy.